So now we're moving into the specific test statistics. First, the so-called diffuse, or as I call them, spatial autocorrelation tests. And we'll focus only on the Moran Xi. And the Moran Xi for residual spatial autocorrelation is essentially the same as the Moran Xi that we saw the other day, except that in the computation of the mean and the variance of the statistic under the null of no spatial autocorrelation, we make some adjustments for the fact that these are residuals and they're not just regular random variables. And as I mentioned a few minutes ago, residuals are already somewhat spatially correlated, so that needs to be taken into account. So if we have the residuals of a regression, let's call them E, then the Moran Xi in matrix notation is what we've seen before. The cross product of EI and EJ multiplied by the weight Wij, that is the same as E prime, where E prime is a row vector, W is a matrix, E is a column vector, so the end result of this is a scalar, is a single number. We standardize it or scale this divided by S naught, which is the sum of all the weights. And then in the denominator, we have a measure of variance, the sum of squared residuals divided by the number of observations. As we discussed the other day, when the weights are row standardized, then the sum of all the weights end up being the same as the number of observations, n. And so then the two n's, the one in the numerator and the one in the denominator, cancel out. And we have this expression, E prime WE over E prime E. This is formally exactly the same as a Durbin-Watson statistic. A Durbin-Watson statistic replaces W by some other matrix. In a lot of textbooks, this is called A, which simply reflects the difference between T and T minus 1. So it's not a full matrix in that sense. It has a different structure. But in terms of the test statistic, it's the same form. We have this ratio of a quadratic form over a sum of squares. And so again, we can carry out the inference in the same way as before. We can assume normality, or we can and derive the exact distribution, or we can approximate the distribution by a normal one, which is an asymptotic procedure. And to do that, we need to get the mean and the variance, and then we use the same approach as before. We take the Moran Xi statistic, we subtract the mean, and we divide by the square root of the variance, and that gives us a z value that we then compare to the standard normal distribution. So in the standard normal is approximately correct as a distribution. This is not exact. As the sample size increases, the approximation gets better. Just to give you an idea of the complexity that is introduced by having residuals rather than the actual error terms, there is a connection between the residual and the error term. And this is textbook econometrics. If you haven't seen this, it's very easy to work out. You just put explicitly the result for the least squares estimator, the x prime x inverse x prime y, into the predicted value, and then you work it out, and then you see that the residual, which is the difference between the observed and the predicted value, so the difference between y, which is really x true beta minus true error, that, and then the predicted value, which is x times estimated beta, that difference is the residual, and then you can relate the residual to the error term. And there's this matrix M, which is what we call a projection matrix. And it's a particular matrix in that it is what is called idempotent, which means that if you multiply it by itself, you get the same thing back. And this is a particular characteristic of matrices that is used a lot to derive distributions. And if you've never seen this before, there's no way for me to explain this in 5 minutes, but basically this results in a chi-square distribution for the sum of squared residuals. And the fact that this M is there, we really are, in a strict sense, we're not interested in whether or not there's spatial autocorrelation in the residuals as such, but we are interested in whether there's spatial autocorrelation in the error terms. And this M epsilon gives us the connection between the residual and the error term. And that connection needs to be kept in there, otherwise we're simply testing residuals. Now you could do this, but it doesn't help you anything, because it doesn't necessarily tell you what is going on with the model itself, which is really the purpose of specification testing. So since we have this connection between the residual and the error term, the mean of the Moran xi for residuals is no longer the same as the one we had for regular random variables. Remember, there was -1 over n minus k, which as n increased got closer and closer to 0. Here it involves the trace of a product of two matrices. The matrix M, which is this projection matrix, which is n by n, and the matrix W, which is our weights matrix. So if you multiply these two together and compute the trace, that is a number that goes into the expected value of Moran xi. And similarly, the derivation of the variance, if you thought it was complicated for Moran xi to begin with, it's even more complicated here, because all these trace terms get in there. And these look very complicated, but there are, in fact, trace is the sum of the diagonal elements. So the moment you can figure out what's on the diagonal, you really don't need to know what's in the rest of the matrix, because only the diagonal elements get added up. So these traces, I'm showing them here to you because they will come back in many other specification tests and test statistics. This trace thing is something that is characteristic of the spatial approach. You don't see this in time series analysis. So these expressions, the trace of MW prime, or the trace of WW prime, these are the kinds of things that we keep seeing over and over in these diagnostics. So the essence of this is Moran xi on residuals is not really Moran xi on residuals, because we're interested in finding out whether the unobserved errors are uncorrelated. So the residuals are just a way to get at the errors. So the mean and the variance will be different from the mean and the variance that you get if you apply the standard Moran xi to residuals. So there's a correction that is necessary for the fact that these are residuals. Once you do this, then the rest is the same as before. We compute the standardized variate, and we compare that to the standard normal distribution. That's a large sample approximation, and we're in business. And this is pretty straightforward. Look at the top. The top is an example of what GeoDa will give you, and we'll go through this in the lab this afternoon. It gives you Moran xi value of 0.2. Remember that, if you may remember, that was also the slope that we saw in this Moran scatter plot that I showed as one of the informal diagnostics. And we find that the z value, after we compute the mean and the variance, this transformation, the z value is 5.8, which is clearly highly significant. So we reject the null. Okay. So at this point, we reject the null. We know that our errors, not the residuals, the errors, are not spatially random, are not uncorrelated. We do not know whether this is because the true model is a lag model, or the true model is an error model, or possibly something else is going on, like heteroscedasticity. This is the Moran's test in R. One thing that we'll point out in the lab too, it's important that you spell out that the alternative is two-sided. The default is one-sided. And in R, you have to be very specific about what it is you use. So you specify a model, you specify weights in the proper form, and then you specify whether your alternative is one-sided or two-sided, and these results are the kind of thing that you get. We'll get more in detail on this in the afternoon. So now we move on to the focus test, the test specific in a framework of maximum likelihood estimation. And as before, we make the distinction between unconstrained and constrained model. The constrained model is the one where all the parameters are set to 0, or where the parameters of interest are set to 0. The unconstrained model, they are non-zero. And just as a refresher, there are, in the maximum likelihood framework, there are 3 ways to approach this. One focuses on the value of the estimate. One focuses on, if you wish, the fit of the model. And one focuses on the score or the slope of the likelihood. And let me just quickly give you the intuition behind this. The constraint is that the parameter is 0. Now, when you estimate a parameter, that's a random variable. So if you get a number like 1, that is not by itself sufficient to say that this is non-zero. What you need to know is the uncertainty associated with that point estimate. So if it's 1 plus or minus 0.001, then you can say, yes, this is not 0. But if it's 1 plus or minus 5, then you can't say this is non-zero. And that's the difficulty. How do we get the standard error? And so each of these test statistics are about comparing the situation that we get when it is truly 0 to the situation that we get in our estimate, and assessing through an estimate of the standard error whether or not this is significantly different. So there are 3 ways of looking at this in a maximum likelihood framework. One is focusing on the estimate itself. How far away is this from 0? Another is to focus on the likelihood. Is this really a maximized likelihood? And a side effect of this is, in the maximum, the likelihood, the slope, the gradient of the function is flat. The slope is 0. So then you can say, well, how different is this slope from 0? And these are the 3 classic principles. And in a little graph, you can see this. This actually uses the maximum likelihood estimation of the spatial error model, or the regressive error model for the Columbus sample data set. The blue line is the likelihood and the value that it takes as the parameter lambda changes. And so you see, as the parameter lambda goes from minus a little less than -1 and moves up, the likelihood keeps going up, and then once you hit 0.54, something like that, then it starts going down again. So our estimate is, let's say, 0.54. The first question is this 0.54 truly different from 0? And that's our first principle. This is what is called the asymptotic t-test, or a wall test. And so what we need for this is some measure of the standard error, or the variance, if you wish, of the estimate, and then we can tell, well, is this really significant, far enough away from 0, from the reference 0? The second principle looks at the value of the likelihood, and how the value of the likelihood in the unconstrained model compares to the constrained model. And the rationale is the following. In the fit of an unconstrained model will always be better than that of a constrained model. I mean, it's always, if you think of regression, if you add more variables, your R-square will go up. Okay. How much does it go up? That's exactly the question. Does it go up enough so that it's a significant addition? So by imposing the constraint, your fit will go down, because in essence, you're taking some freedom away. So you're forcing the data, you're forcing the model to have 0 as the parameter. If you don't force it, the parameter will be non-zero, so the fit will be better, but how much better? Is it significantly better, or really not that much better? And if it's not that much better, we cannot reject a no, because then in essence, the fit of the constrained model and the unconstrained model are the same. But if it's significantly better, then the unconstrained model is much better than the one with the constraint, so we reject the constraint. The constraint is no good. So how do we know whether this is significantly better? We need to have some measure of the standard error, so to speak, or the variance of the maximized likelihood. So if we have that, then we can tell, again, if you look at the point up on the graph, the point here, that yields us a likelihood of following the red line, and then the constraint point gives us the green line. This difference between these two is that a significance difference. That is the bottom line. And we can, again, assess that if we have some measure of the variance of the maximized likelihood. And then the third, and that's going to be the likelihood ratio test. It compares the likelihood of the constrained model to that of the unconstrained model. And then the third principle looks at the slope of the likelihood function. In the maximum, the slope is 0. If we impose a constraint, we're not going to be in the maximum, so the slope will not be 0. Same question again, how non-zero is the slope? So if it's just a little bit non-zero, then we do not reject the constraint. But if it's a lot different from 0, then we reject the constraint. Same kind of question, how do we know how non-zero it is? We need some measure of the variance of this slope. Now, as it turns out, because this likelihood is derived from the data, it's a random variable. So the likelihood has a variance, the slope of the likelihood has a variance, and so on. So these tests, and this particular test will be called the score test or the Lagrange multiplier test. It's based on the gradient of the likelihood function, and it checks whether the gradient is significantly different from 0 in essence. So each of these are different ways to approach the problem. Asymptotically, they're all equivalent. They're all the same. In finite samples, they tend to show differences. And we'll talk about that in a minute. So the principle is relatively straightforward. In one case, we get an estimate of our parameter, and we basically do a significance test on that parameter. That's an asymptotic t-test or a wall test. In the second case, we fit the model under the null. That's the constrained likelihood. We fit the model under the alternative. That's the unconstrained likelihood. And we compare these two likelihoods in a likelihood ratio test. And in the third case, we run the model under the null. We don't have to run the model under the alternative. And we look at what the slope is of the likelihood function. And if this is significantly different from 0, we reject the null. So what are the advantages and disadvantages of each of these approaches before we get into the specifics? The asymptotic t-test, we have to run the spatial model. So that is an extra complication. The likelihood ratio test, we have to run two models, both the spatial model as well as the one without the space. The Lagrange multiplier test or score test, we only run the model under the null, which is nothing but our standard regression model. So the attractiveness of the Lagrange multiplier approach is that you don't have to estimate the spatial model. And this is particularly attractive when we get into nonlinear models like spatial probit and things like that. You never have to go that route. Okay. The price you pay for this is that the power of the Lagrange multiplier test tends to be a little less than the power of a likelihood ratio test. And this is because a likelihood ratio test, if you think about it for a second, it uses information from two estimation procedures. And the Lagrange multiplier test only uses one. So it's always about information. So now that we have established the principles, let's move to the some applications. So we have a wall test, likelihood ratio test, Lagrange multiplier test. Asymptotically, they're equivalent. In small samples, in stylized situations, and I will comment on that later when we have specific applications, the order that you find in small samples is Wall test is the largest, likelihood ratio is in the middle, and Lagrange multiplier is the smallest. What does this mean? It means that there is a possible situation that you reject the null using the Walt or asymptotic t-test, and you would not reject the null using a Lagrange multiplier test. At the margin, you could have a situation that the p-value for your asymptotic t-test, say, is 0.05, and for your Lagrange multiplier test would be 0.07. Remember, the inequality here pertains to the magnitude of the test statistic. The larger the test statistic, the smaller the p-value. So if this one is larger, the Wald is larger than the Lagrange multiplier, it could be that the p-value of the Wald, it will be that its p-value will be smaller than that of the Lagrange multiplier test. And it could be that one lets you reject the null and the other one does not. What do we do in a situation like that? It depends on your objective function. If you want to be careful, you will go with the alternative and then do a model validation from that point of view. If you are a purist, then you could say, I do not reject a null, and everything is fine. If you don't want to estimate a spatial model, you know what you do, right? You say, my Lagrange multiplier test was 0.07, I don't have to do anything. But it is something in practice that is a red flag. It suggests that something is going on. You may not remember, but when I formulated this, I said, under stylized situations, this is the order that you get. What does that mean? It means the absence of other sources of misspecification, one of which could be, say, a strong degree of non-normality. In the presence of a strong degree of non-normality, these things will tend to get mixed up. Also, in the presence of strong heteroscedasticity, these things will tend to be mixed up. So it's not unusual at all in practice to find that this order is not satisfied. Again, what does that mean? It suggests that there are other sources of misspecification that may affect your results. In the theoretical framework, it should not happen, but in practice it does happen because we don't work in this stylized world where we just control for one possible source of misspecification. In fact, any number of things could be going on and will invalidate this. So I like to point this out as yet another element in your specification search. If you see that this order does not follow for your results, if you estimate multiple models, then it suggests that maybe you should revisit the model, think about the weights matrix, think about the functional form, and so on, because those are likely the causes for the this order is not invalid because something's wrong with your spatial tests. It's invalid because the statistical framework in which the properties of the spatial tests were derived is not holding up. So it's like a house of cards. If you take the bottom out, everything falls down. It's the same thing. Okay, very quickly, the three specific tests. This is pretty straightforward. The wall test is asymptotic. It focuses on the difference between the estimate and the constraint, which is in this case 0. So we do need some measure of a variance, and the test statistic is, as usual, is the value of the estimate divided by the square root of its variance. And asymptotically, this is standard normal. If you square it, so the asymptotic t-test is actually not a t-distribution because it's asymptotic. The t-distribution converges to a normal distribution. So that is often a source of confusion. In practice, there is a debate whether or not you should, in smaller samples, whether you should use the asymptotic normal distribution or use a t-distribution instead. There is some evidence that in some cases, essentially what you do is you adjust for degrees of freedom. So you use n minus k as a degrees of freedom. As n becomes very large, the difference between n and n minus k is negligible. In smaller data sets, it may make a difference, but these kinds of adjustments, you know, the formal properties of these are often very difficult to derive in any but the simplest situations. So my advice is don't work with small data sets, but you know. The wall test is often referred to as the square of this. So the square of the asymptotic t-test, because it's a square of a standard normal, will be a chi-square with 1 degree of freedom. So that is the way, this is how you make it comparable with the Lagrange multiplier and likelihood ratio tests, because those are also chi-square with 1 degree of freedom. So in terms of this inequality that we just talked about, don't use this one, but use its square. So don't use the t-test as it is, but square it and then compare that value to the value of the likelihood ratio test and the value of the Lagrange multiplier test. For the likelihood ratio test, we need to do 2 estimations, which is additional burden, but in return for that, we get very good power. In many situations, the likelihood ratio test turns out to be the most powerful one, and as I just mentioned, the intuition of this is that you use more information, and always as you use more information, you'll get better power. So we need 2 estimates, then we take the difference between the log likelihoods and multiply it by 2, and that is again a chi-square. So that's pretty straightforward to do. It is also a solution to a problem that we often encounter in practice. In a lot of these spatial models, as we'll see later this morning, the maximum likelihood estimation, it's one thing to maximize the likelihood function. It's another to come up with the second order partial derivatives, which is what you need to get an estimate of the asymptotic variance matrix. So to do the asymptotic t-test or the wall test, we need this asymptotic variance that comes from this asymptotic variance matrix. So if you don't have an estimate for the asymptotic variance matrix, you're out of luck in terms of a t-test. You don't have the denominator for the t-test, so you can't carry it out. The solution to this is if you can maximize the likelihood, then you can compare that likelihood to the one under the constrained model. So the way you test for other than just a spatial parameter is you run a model, say, with 4 variables, and then you run a model with 3 variables, and you carry out a likelihood ratio test on those 2 models. So this is something you would do if you do not have an estimate of the asymptotic variance matrix, which in some cases is extremely difficult to derive. So that's, if you, some of the numerical solutions to estimate maximum likelihood models for very large data sets don't have an asymptotic variance matrix, and they use this approach to do significance testing on the parameters. So you basically rerun the model with a different combination of variables and then do likelihood ratio tests between the 2 models to assess the significance. And then the last one is the Rao score test or Lagrange multiplier test. The reason for these 2 names is that it was derived, one was derived in the econometric literature and one was derived in the statistics literature. They come at the problem slightly different, but they come up with the same solution. So depending on whether you're a statistician or an econometrician, you will tend to use Lagrange multiplier or Rao score test to refer to this same principle. So as we saw, it only requires estimation under the null, which is the model, the standard regression model. So you run your regression model, take the residuals, plug them into this test, and the test has a specific alternative. So you can derive a Lagrange multiplier test for a lag alternative and for an error alternative. Both of these require likelihood functions, which we'll talk about later on this morning. You need the score. The score is the first partial derivative. The information matrix is the second partial derivative. This is all pretty standard stuff, and you just plug in the proper expression. So The challenge is for a particular alternative to formulate a likelihood function to be able to come up analytically with expressions for these partial derivatives, and then you plug in the value that you get under the null and just compute the statistic. So if you do a little bit of algebra, you find that for the case of the spatial error alternative, this is the expression you get, which is actually a rescaled Moran's I. If you look at this carefully, in the numerator we have E prime WE, which is exactly what we had for Moran's I. In the denominator of the numerator, I should say, we have E prime E divided by N, which is exactly what we had in Moran's I. What we don't have in there is this S0 that we had with Moran's I. But instead, we have this T, which is the trace of WW plus W prime W, the trace of the product of these weights matrices. And these can be seen, these traces can be seen to be essentially the sum, one of them is the sum of the square of the elements in the weight matrix. So they're all related to the overall structure of the weights matrix. They're summaries of the structure of the weights matrix beyond simply the S0 that we had in Moran's I, which was simply the sum of all the elements of the weights. These are sums of squares of the weights and sums of cross products of the weights. That's essentially what these traces end up being. So in essence, it's very much like Moran's I. In fact, asymptotically, the two are equivalent. So as your data set grows very large, the Lagrange multiplier test and Moran's I are the same. In small, finite samples, there are slight differences between the two. The advantage of the LM test over Moran's I test is that it has a specific alternative, which Moran's I does not. Did you have a question? You look puzzled.
Yeah, but I don't want to ask the question.
Okay. Why not?
Because I'm.
We won't tape it. We'll stop the tape.
I know. I was harking back yesterday about when you get a sum and a product of terms, you get collinearity almost guaranteed. So I was looking just internally to the trace. Those are sums and products that so triggered that thing in my head. Now I wish I hadn't opened my mouth.
No, but they're not parameters to be estimated. Okay, W is known, so these can be computed. In fact, they can be computed without actually doing the matrix multiplications, because you one of them. Let's see if I get it right. Yeah, the first one, if you see W prime is every row becomes no, it's the second one. W is the row times the first column. And so these are all the matching elements, the cross products of these elements that go into trace. So the first row times the first column, the second row times the second column, those are the elements that go into the diagonal. And if you work it out, and you can do it on a piece of paper, you'll see that one of these is the sum of the cross products of the Wij with Wji, and the other one is the sum of the squares of the Wij. So rather than making this big matrix and getting its transpose and multiplying the two together and then pulling out the diagonal and summing those elements, you don't have to do that. You can just simply add these squares up and you have the trace. So this is what GeoDa does. It's very fast, and this also allows you to do this for very, very large data sets because there's no actual matrix multiplication involved. And that makes it more attractive than a Moran's I for very large data sets. I didn't get into the technical detail, but if you go to the readings, you will see these monsters of expressions to get the variance of Moran's I for residuals, and they involve multiplications of big matrices, and there is no way they involve the multiplication of M and W. And these are big matrices, and there's no way to get around that and to simplify that. So for large, from a practical point of view, from a computational point of view, for large data sets, to get the variance of Moran's I is going to be a burden. And that's why, as you'll see in the lab this afternoon in GeoDa, there's an option to turn that off and to say, I don't want the variance of Moran's I, because my data set is too large and it's going to take forever to compute it. Instead, I'm just looking at the Lagrange multiplier test. Since this data set is large, for all practical purposes, the two are equivalent, and computationally, this is a lot easier to do. You don't actually have to multiply any matrices. The things to watch out for, and I think you will start appreciating this, the major difference in spatial regression analysis is these matrices. You have to worry about weights matrices, this I minus rho W matrix, inverses of this matrix, and determinants of this matrix. So computationally, anytime you have to actually do this, it's going to be a burden, and it's going to limit you to smaller data sets, because it simply can't be done. So anytime you can work around this, and you have an alternative procedure that doesn't actually require these matrix manipulations, then those become the preferred techniques for very large data sets. And for example, in terms of estimation, that's the strong argument in favor of general methods of moments estimation procedures rather than maximum likelihood. Even though maximum likelihood is superior in some sense, in very large data sets that superiority kind of disappears, and the GMM methods are so much easier to implement. You don't have to mess with these matrices, so that's in their favor. Same thing here, relative to Moran's I, to compute the variance. In Moran's I, you have to actually multiply the matrices. Here you don't.
Can W and W prime W be added unless it's a square matrix?
It's always a square matrix. It's the weights matrix. You know, if it is not, then it's an issue of the dimensions. The dimensions will become different. So then the trace notion is a notion that pertains to square matrices, because it has to be the diagonal. Okay. So we apply the same principle. Again, if you're interested in the specific technicalities of the derivation, I refer you to the readings. It's essentially a bunch of matrix partial derivatives. This is a lot of fun if you know how to do it. If you don't, it's just totally obscure. But if you work through these steps and you just plug in this core and you plug in the information matrix, then this is what comes out. And again, this is similar to a Moran's I, but now rather than having a cross product of the residuals only, we have a cross product of residuals with the dependent variable y. So we have this E prime wy in there, and then we have a different correction. The T1 still has the trace expression in there that we just talked about, but it also has this other thing which looks formidable, but it's a residual sum of squares of the spatially lagged predicted values on the original x variable. So WXB is, XB is the predicted value in the regression. W makes that into a spatial lag. And this M thing is our projection matrix, and this WXB prime MWXB, if you work out the algebra, is in fact the residual sum of squares. So you can get this by running an extra regression, or you can do the matrix algebra.
Is the sigma square there in the formula of the variance in the error term?
Yes, the sigma square is the same one as before, E prime E over N. So it's it's a consistent estimate for the variance. It's not a small sample estimate. It's not divided by N minus K, but it's divided by N. So again, this is pretty straightforward to compute. It doesn't really involve any big matrices. You can avoid this. And so now we have two tests in hand. The problem is that each of these, and this goes back to what we discussed earlier, each of these has power against the other alternative. So if you carry out a Lagrange multiplier test for an error alternative and you reject the null, you could be rejecting the null because the proper alternative is the lag model. And of course, you will always reject a null more if the proper alternative is the error model. So if you compare two situations, one where, and you can do this in a simulation experiment, one where you generate an alternative as an error model, and one where you generate an alternative as the lag model, the test will always do better for the error model than for the lag model. But in practice, you don't know. You have your regression, you have your residuals, you run the test, you reject a null, and you don't know which really is a true alternative that is behind this. So there is a way, and the asymptotics are kind of complicated. You can read up on them in the references if you're interested. But the intuition is the following, that we will take out, in some sense, filter out the effect of the other alternative on the test statistic. And then we end up with a robustified test statistic, which is, in some sense, purified of the other alternative. So these are the robust LM statistics. I will spare you the expressions. They're very complicated. But they basically start with the original statistic, and then say you end up with a value of 6. And then you carry out a correction that is due to the effect of the other alternative, say the lag in case of the error. So you take out something. So instead of a 6, it becomes a 4. And then the 4 is used in the test statistic. And what happens typically is that you have the LM test and the error and the lag test, and you do this correction, then one of these will stay significant and the other one will not be significant. And that then points you into the right direction of the proper alternative. That's the rationale behind these robust LM tests. One thing to keep in mind is never do these tests if you don't reject a null with the initial LM test. It's really a robustification of the initial test. If the initial test is not significant, for a variety of fairly obscure reasons, the adjustment is not valid. So you can have a situation, and in practice, this comes up more than you think, where the LM tests, the original LM tests, do not reject a null, but the robust ones, or one of the robust ones, does. That is not a valid situation. Ignore that. So that gets us to, well, this is the same thing. We'll get back to this in this afternoon. So in GeoDa, you get both the original test for lag and error, as well as their robust counterparts. But I'll revisit this in a minute when we talk about specification search.
And a question, actually, I think that might answer. What if you are considering both a lag and error model?
Together.
Together.
Then well, there is a test which has 2 degrees of freedom, which looks at both of them. But this test also has power against single alternatives, so it's a little tricky. So you, again, it's the same situation. You reject a null here. That doesn't mean that necessarily it's a double model. It could be a very strong single model. The procedure in practice one follows is you start with 1 and you test for remaining misspecification. And then you can move on to a higher order model. However, as we discussed yesterday, you might be better off revisiting the first model and maybe specifying a different weights matrix. Okay, so I'm not a big fan of these SAR or SARMA models. I tend to, and in my experience, most of the time I've been able to get rid of that problem by respecifying the weights matrices. In some instances, you cannot get rid, and then I prefer to use a robust, white type adjustment of the standard errors rather than putting even more structure in the error term. And what that does is when you look at the GMM estimation, it adjusts the standard errors for this uncertain spatial correlation that you might have in the error term. But we'll revisit this in a minute when we talk about specification search.
Dr. Anthony, do you have time to go back to that last table? And I was just looking at the lag and the error values.
Mm-hmm.
Now in this, you would accept that error is the contributor?
Yeah, well, this is running ahead a little bit, but I might as well do it now. So what we see here is we look at the Lagrange multiplier for the lag is 20.5, and for the error is 23.6. So both of these are very high values and reject the null clearly. Right? Then we move to the robust tests, and we see that the robust lag, in fact, the way to think about this is we start with 20.5, we correct for error, and it drops down to 1.2. In the error one, we start at 23, we correct for lag, and we end up at 4. Now the 4 is marginally significant. The 1.2 is clearly not. So at the second stage, we cannot reject the null using the robust lag test, but we can, at 0.03, using the robust error test. This case, it would point to an error as the alternative.
The SARMA is more.
The SARMA is not robust. The SARMA is these two, is a combination of these two. It's not the sum of these two. In some other situations in econometrics, you simply take the sum of the LM test. That's not the case here.
What are the values of the lag versus the error? I mean, they're all highly significant, but the difference between the values don't seem to be that much, or is that just not really that significant?
Well, in this particular example, it is not that much, but in some other examples, in fact, I have one later on, the one is clearly significant, the other one is not. The situation, I think, that Joe referred to earlier on is one, even at this stage, the robust statistics are not that different. And that is a situation that you do encounter in very large data sets. And my take on it is that it suggests that you have other things to worry about. And for example, the weights matrix or the functional form or the model itself. See, one thing that is very subtle is that this whole framework of specification testing is really built in a context where not too much is wrong with your model. So you can think of a situation where basically everything is right except this one thing that you are testing for. Now when that is not valid, then all bets are off. And in fact, some of the properties of these tests no longer hold. And one thing that I like to point out often in practice, I've seen, thousands of these printouts, literally, is that when you get these kind of weird results, check the fit of your model. And more often than not, the R square to begin with is, 0.05. So which means that basically your model is not explaining anything to begin with. And then, a lot of these specification tests will go haywire because underlying them is that in some sense this y equal x beta plus the error term has to hold somehow. And if your model doesn't fit, then clearly something else is going on, and then your first priority should be to get a better model, and then revisit the specification test at that stage. You'd be surprised, when you see these really weird things, look at how well your model does to begin with. If it does really well, then of course it's some, it could be some subtlety in terms of the spatial part of it, specifically spatial weights. But more often than not, you will get these situations when the initial model is not very good to begin with.
Is there a way to figure out when a model that fits very well is spurious?
The question is there a way to figure out whether a model that fits very well is spurious? That's a very difficult question. In theory, it's not that difficult because you control everything. But in practice, it's difficult because you don't really know, what the correct model is. So you do have some sense, if you've done this a lot, you have some sense of how these different diagnostics appear together, for example, so that you can have some indication that when you have two completely contradicting tests, for example, that might suggest some spurious relationship. But in space, the counterpart of the time series spurious regression is not that simple. It's actually quite complex because you have a different parameter space. And things, there are one or two articles in the literature that try to make that connection, but it's still, it's very limited. So I can't give you a good answer because I wouldn't say I don't know how to do this, but I take a very practical approach and try to get some sense of how the model does and from a number of different diagnostics. But the specific question you're referring to, the counterpart of that in the spatial regression is very underdeveloped.
There's one more question that someone asked about the performance of the tests in comparison to different sample sizes, with small samples and large samples.
I think the question is really how large is the data set that you described should be used, or how small should we avoid?
Yeah. In fact, this came up in my individual conversations as well. How large is large? When do the asymptotic properties kick in? And this is test-specific and method-specific. Some of these tests, for example, Moran's eye, has already very good power and is, for all practical purposes, unbiased for 30 to 40 observations. Some others, like the Lagrange multiplier tests, require, this is a rule of thumb, this is not a hard and fast answer, around 100 to kick in. Some others, which we do not discuss here, but you can find them in the readings, for example, the Collegian-Robinson test, which is a moment-based test. It uses cross products of the residuals. That test statistic requires much larger samples, several hundreds to over 1,000, before its asymptotic properties kick in. And a rule of thumb is if you have these moment-based statistics, they will tend to require larger samples. Because what they are essentially, the intuition behind them, the motivation for them, is to use residuals as proxies for the actual errors. And as your sample gets larger and larger, that becomes a more legit thing to do because several summary characteristics of the residuals will start to mimic the summary characteristics of the error terms. Like in the proofs, if you dig into the proofs, you see that certain types of cross products of x's with the residuals mimic the properties of cross products of x's with the error terms. And you get that with large samples. You do not get that with 40 or 50 observations. So the only way you can find out is by doing simulations. And as I mentioned yesterday, in the spatial domain, there's really nothing like the range of simulation experiments that have been done in traditional econometrics. So in some of these for some of these questions, I don't really have an answer. I can just tell you what my experience has been in running many simulation experiments and comparing the different test statistics. Bottom line is moment tests, very large, 1,000 more, it should be fine. Moran's eye is great. You can even use it in smaller samples, 30, 40. LM tests around 100 and starts performing well. But these are just rules of thumb. I'm not saying that at 99 it doesn't work, and at 101 all of a sudden everything is fine. It doesn't really work that way, but there are these kinds of rules of thumb. So let's spend 5 minutes on specification search. There are two main approaches, and in fact I can do it in 5 minutes because I've said most of what is relevant here. Two ways to proceed: forward and backwards. Forwards means you start with a simple model, the constrained model. Typically this is a linear regression with ordinary least squares. You use the residuals, you carry out a test, you move on to the next model. Then you repeat the whole procedure. So you estimate the model, look at the residuals, carry out a test, proceed to the next model. And you do this until you have taken care of all the problems, so to speak, until remaining tests for autocorrelation or heteroscedasticity or whatever you can think of no longer reject the null. So you have built so much structure into your model that what remains in the error term is just noise, and then you stop. The backward way is the other way around. And this is known in time series analysis as the Hendry way. You start from the most general model you can possibly think of. So in our case, that would be a spatial lag model with spatial autoregressive errors and heteroscedasticity, or whatever you can think of. And then you start to test constraints on these models, and so you start dropping. You can think of this as stepwise regression in some sense, where in one you start and you keep adding variables to the model. In another one you start with a big model and you keep dropping variables from the model. It's the same kind of logic. What are the pros and the cons of the two procedures? The forward process, you have the pre-testing approach. In that, let's say you do an LM error test. So there is a p-value that is your decision point. Let's say it's 0.05. So that means that in 5% of the cases, you could be wrong. So if you think of this as a branching process, you start with the residuals, you do your test, then you reject the null. 95 of the cases you're right, you estimate the error model. 5% of the cases you're wrong. So when you do your inference for the error model, you have to take into account that you're already in a branch and that you're already in a chance of 95% of being right, but a chance of 5% of being wrong. And that is the pre-testing problem. You have to adjust your p-values. There's a little bit of analytic work on this, but it's very complicated. And for any kind of complex model, it becomes intractable, especially if you do it more than once. And that's the problem that I referred to earlier today, and that is that the p-values are not reliable. The problem with the backward strategy is that you have to estimate the most complex model to begin with, which may be a challenge. Okay. Then we end up with our decision strategy. In a nutshell, we start with the OLS residuals, and then we proceed through a series of tests, which I will give you in a minute, because we'll stop here, put in a new tape, and then we'll start with that. But I don't want to have a break yet, because I want to finish here before we go into the estimation.
Are you off record now?
We're off the record, right?
Sometimes folks suggest mixed model, hierarchical model, nested model, so that the greater container kind of soaks up some of the spillover or spatial diffusion and so on. This suggests that you're running just kind of a single equation regression and then drilling down from there. An alternative would be to get rid of any sort of correlated error by going with this hierarchical linear model kind of approach, I guess. Do you have a feel for which is the better way to go? People ask these sorts of questions.
I don't think it's a matter of better. I think it's a matter of what is appropriate in different contexts. As we'll see tomorrow when we talk about heterogeneity, you can have combinations of the two. And so even in a multi-level model, you can have spatial correlation in the error term, for example, or you could have a lag model. The question then becomes, at which of the levels is it most appropriate to build in this structure? Do you build in, say, spatial autocorrelation at the micro level and then not at the higher level, or the other way around? Do you keep the micro level uncorrelated and then have the aggregate encompassing level be correlated between them, or both? And so you can come up with really complex covariance structures. The question then is, how much do the data support in terms of these complex structures? I don't think it's a matter of better. I think it's a matter of what are you looking for in your models, what types of conclusions are you trying to draw, and how much is heterogeneity a problem? I mean, here, today, we're basically assuming heterogeneity away. Tomorrow we'll bring it back in. And so then we have all kinds of issues of structural instability. Is it discrete? Is it like a fixed effects type of structural instability, which is also some of the logic in the multi-level models, or is it a random type of structural instability, which is then a different way of modeling things? But in each of these same problems come back in, because it's not because you're making it a multi-level model that the spatial autocorrelation necessarily goes away. This is something that I need to stress very often also in a panel data context. It's very standard to use spatial fixed effects and then to assume that that takes care of the spatial autocorrelation. Not necessarily. Sometimes it does, sometimes it doesn't. So these other models as solutions to spatial autocorrelation, that's not really the proper way to put it. They're alternative specifications. The spatial problem does not necessarily go away. It can, if you're lucky, but it does not have to go away.
Do you have any general comments on parsimony? You know, how big can models get before interaction affects it?
I like parsimony. That's why, I'm not a fan of these higher order models. I like to keep it simple if possible. Simple models are easy to interpret. Complex models, especially hierarchical models, become very difficult to interpret because there's so much going on in terms of interaction that it's almost, the intuition is gone.
And they tend to not predict as well out of sample, isn't that?
Well, I mean, that's really a different question, because once you're out of sample, the question is really how representative is your sample of the out of sample. So if the structure completely changes, then no matter what you do, you'll be off, because you've been estimating your model on the wrong data, so to speak. So that is again something you don't really know. I mean, you can test, you can check, you can have diagnostics, but you don't really know when you predict something out of sample whether you're assuming that the structure is the same.
But don't more complex models give you more chance of overfitting?
Well, yeah, and they give you, the more you assume, the more you have a chance to make the wrong assumption. That's my strongest argument in favor of parsimony. But you pay a price, because one thing that we won't get into today, but in some of the more recently developed techniques that are robust, so-called, the price you pay is that you get greater imprecision. So you correct your standard errors for all these possible problems, which sometimes makes them so big that nothing is quote-unquote significant anymore. So then, what it's telling you is that the data are not supporting the type of model that you're trying to estimate. That's always the way I bring it back. So let's visit this decision tree here then. Which is very simple, and in fact, I would say it works in most cases, but not all cases. So we start with a OLS regression, and we look at the basic Lagrange multiplier diagnostics, the LM error, LM lag. Ideally, neither of them rejects the null. Okay, then you just do what you always do. Stay with the standard regression software. No need to worry about anything, right? And as I like to say, this happens in about half the cases, maybe, roughly. So then, roughly. The other case is, the other good situation is where only one of the two LM statistics rejects the null. So one is significant, the other one is not, then it's a clear choice. That alternative that is rejected, for which the null is rejected, is the one that you pick as the alternative model. It gets trickier when both LM statistics reject the null, and this happens more often than you might expect. It's fairly common, especially in large data sets. The intuition behind this is that in large data sets, you have so much information that suggests even small deviations from the null, so that the tests have power again, in that sense. So the tests detect even the smallest deviation from the null, so they are significant. They're both significant. Then we move, then and only then, do we move to the robust forms. So as I mentioned a few minutes ago, never start with the robust forms. Always first check the standard LM test and only then move to the robust forms. And then again, in most situations, I would say, I'm just saying 90% maybe, there is a choice. Sometimes it's clearer than other times. Clear meaning one is clearly significant, the other one is clearly not significant. There are situations that I've seen and run into fairly, not that often, but often enough that you have to think about it, where the difference between the two is very marginal. And that, I would say, is typically a situation where there's much more going on. It could be strong heteroscedasticity. It could be that the functional form is not appropriate, that there are structural breaks in the data that you are not taking care of properly in the model, and so on. So the way I would put this is a situation where you don't go full blast ahead and say, okay, the lag is just a little bit better than the error, let's just go with lag and forget about error. Okay? It's a situation that provides evidence that a lot is going on that is of a spatial nature, but you are not necessarily able to distinguish what it is. And so that's a tricky situation. Luckily, at least in my experience, it doesn't happen that often. It seems to be happening more frequently as we are pushing into really large data sets. For example, we tend to have this kind of problem with hundreds of thousands of observations. And that is something that we might need to look at. It may have to do with just the nature of the test statistic. Moran's I is another one. Almost any data set of that size, 100,000 or more, will have a significant Moran's I. And that has really not so much to do with spatial autocorrelation as with the nature of the Moran's I. The variance is of such a form that it tends to become very small as the sample size increases. And so that is something that then artificially gives you significance. And that's something that we need to think about in terms of possible correcting the statistic. But this is very new terrain. It's only fairly recently that we start to see applications of these techniques in truly large data sets. And we may have to rethink how we approach this. But in anything, I would say, from several hundred to several thousand, it works fairly well. It's one, in this recent work that Nancy and I have been doing, where we're really pushing in terms of size of the data set, that we see some weird things. And I think that may require some more work. So then this example again that we just saw, the decision rule, both LM lag and LM error are significant, we reject them. Then we look at the robust ones. One is 26, one is significant at 0.05, so we can reject the null under the robust LM error. We do not under the robust LM lag. So then we should say the spatial error model is the suggested alternative.